Welcome back to Unit 5. We are zooming into the end of the unit. And before we talk about fundamental theorem of calculus, which will be our last topic, in this video, we're going to go over two really quick skills that come up often in free response questions on the AP exam. The first skill is the trapezoidal approximation method, which you learned about last night. And then I'm going to show you how to find the average value of a function. And then we're going to put those two simple skills together in order to solve some application problems. So first, just to jog your memory, this is what the trapezoidal approximation method looks like. It's a formula that you need to memorize. You can memorize this version or this version, and it's a way to approximate the area under the curve that's slightly more accurate than LRAM or RRAM. So why am I bringing it up now? Well, we're going to use it in our application problem at the end of this video, but I also wanted to point one thing out that Patrick's video last night didn't emphasize. Look at this graph, and looking at the area of the trapezoids and the area that should have been the area under the red curve, answer these two questions. When does the approximation yield an underestimate? When does it go over? And how do your answers to those questions compare to the answers for LRAM and RRAM? Right, so hopefully you saw when we're using the trapezoidal method, if the function is concave down, your two trapezoids are going to sit under the curve, and that's going to be an underestimate when it's concave down. When the function is concave up, your trapezoids are going to sit on top of the function, and it's going to therefore overestimate. The difference is with LRAM and RRAM, we didn't care about concavity. LRAM is an underestimate for an increasing function and an overestimate for a decreasing function. RRAM is an overestimate for an increasing function and an underestimate for a decreasing function. So I just said basically 6 facts, all of which you need to memorize. If you need to hear them again, rewind and make sure you can pick out the 6 facts, the underestimate and overestimate for each of these 3 different strategies. Okay, if you know those, you're solid on those, you're ready to move on to the next skill, which is finding the average value of a function. So first of all, it's really important that you understand what this means. I know there's a distracting formula on the screen and a pretty picture. Don't look at those for a second. Just think about these words. What does that really mean to find the average value? Well, if you think about it, the function is f of x, and when we talk about the function, we're actually talking about the y value of the function. So when we say find the average value of a function, we're really talking about the average y value or height of the function. This is going to sound obvious when I'm sitting here explaining it, but trust me, it could end up confusing you when you're trying to answer a problem that's an applied problem, so make sure you're really solid on that connection. I'll give you a visual to help. Here's a weird function in Desmos, super weird. I tried to make it just totally random. But looking at the graph, we can see that from -10 to 40, the graph is more or less somewhere between 20 and 30. The y values of the red function, right? That's the red function. The question is it closer to 30 or closer to 20? We don't really know. If we were kind of talking about this, I don't know, let's say it measures the amount of money in your bank account. During this month, do you have closer to 30 or closer to 20? On average, how much money do you have? You can see the blue line going up and down. This is what I want you to visualize the average value. There's some y value here that is kind of a good description of what the red function is doing on this interval. That's what we're trying to find. Now, why does that have anything to do with integrals? It's not immediately obvious what it has to do with integrals. We're really just looking for a y value. But there's actually a very clever way that you can use an integral to figure out exactly what the average y value should be in this range. It turns out that if you take the integral of the area under this function, so the integral from a to b, and you multiply it times 1 over b minus a, and b minus a you should think of as the distance along the bottom of this area, then that number is going to equal the average height, which you can think of as this blue line. This should not be obvious to you, but there's actually a really good reason for it. And I'm going to refer you to YouTube to just a 2-minute explanation of why that works. So you're about to see a link on the right side of your screen. Watch that link. I promise it's 2 minutes. It's really going to help you understand this function. And then come back and answer the question at the bottom. How does the average value related to the area under the curve and to the area under the gray rectangle? Okay, beautiful. Hopefully that makes sense. In a second, we're going to practice finding the average value. But before we do that, it's important that I connect the average value to a really important fact in calculus. It's called the mean value theorem for integrals. It turns out, and this is just a fact, it's a little hard to understand how you're going to use this, but it's something that you should know is true. It turns out that if you're talking about a continuous function, or at least a function that's continuous between a certain a and b value, and let's say this continuous function has an average y value, a y value height that's more or less what it usually is in that range, then there has to be at least one x value, which we're calling c. It's going to be an x value in between a and b. And for this special x value, there has to be an x value that has a y value that is exactly the same as the average of the function. In other words, if you have an average value between a and b, the function has to actually cross that average value line. There has to be some point where the value of the function, its y value, is the same as the average that you calculated for the whole range. Okay, store that away as a fun fact. It's the mean value theorem. You should recognize the picture. Let's go back to what we were talking about with areas. You're going to calculate the average y value of each of these three functions on the interval 1 to 3, 1 to 4, and 0 to pi down here at the bottom. How do you do this? Well, I'm going to have Patrick JMT model an example for you. This video is just 3 minutes. It's linked in your video, so I'm not going to have you watch it on screen, but go ahead and click on the link to this video. Promise it's just 3 minutes. It'll teach you how to do this, and when you come back, you should be able to answer these 3 example problems. Great, so hopefully that should seem pretty easy to you. Go ahead and try mimicking what he did in the video for examples 1, 2, and 3. This is what the work for number 1 would look like. This notation in the middle is something you may not have seen before. The way that I notated this was I took the antiderivative, and this bar says I'm going to evaluate the antiderivative at 3, which is what negative 9 over 2 is, and then evaluate it at 1 and subtract the 2. It's a useful notation so that you can show your work for an integral in one step instead of having to write antiderivative off to the side. And you should probably start to use this notation if you don't already. Number 2 looks like this. Double check that you have the correct work. And number 3 was nice and quick because actually this is a known integral. Once you set it up, the integral from 0 to pi of sine of x is just 2. So nice. Okay, this is a totally easy skill. This is half of what you need to know for tomorrow, if not more. And next we want to take this skill and apply it to some more AP-worthy questions. The example you see on the screen is a very common free response question. In fact, I think I remember something like this being on the AP exam whatever million years ago I took it. So the reason this is a useful question for the AP to use is because using a data table in a real-world situation, they can ask you to basically prove that you understand how all the major concepts in calculus connect to each other. Let's try. So we're given a data table. And first thing you want to do is just recognize that the input values are in minutes and the outputs are in degrees Fahrenheit. So W stands for temperature. And now we read the situation. The temperature of the water in a tub at time t, each of these times, is modeled by a strictly increasing, twice differentiable function. So that means increasing, the numbers are going up, it makes sense. Twice differentiable means it's smooth and continuous, at least, among other things. And it now says that W is measured in degrees Fahrenheit and T in minutes. We already knew that. Now, at time 0, the temperature is 55, and the water is heated for 30 minutes, beginning at time 0, so it's heated continuously. These are the values given. So basically, this paragraph is just telling us what we already knew. So those of you who get intimidated by words shouldn't, because all of the things that it just said, we knew just by interpreting what this table meant. So now we're ready to start the actual problem. Section A says use the data in the table to estimate W prime of 12. And then it says, show your work and explain yourself and all that stuff. So I'm going to cover up all the words here so we can focus really on what this means. The trick to being able to answer this question, because this is probably not something you've done before, is to really understand what it's asking you for. What do you know about W prime of 12? Exactly, it just means the derivative of the W function at time 12. Now, normally that's easy to find if we have an actual function, but we don't have an actual function, so I can't just take the derivative, which means there's some other connection I can make here. What else do you know about the meaning of the derivative at time 12? Precisely. Another way to understand what the derivative is to say it's the instantaneous rate of change. You could also have said it's the slope of a tangent line, if you like. Now, if this seems like a trivial thing to be spending time on, hold your judgment for a second, because the next is a bigger leap that we have to make. So, if we don't know what the exact function is, it's actually not possible to find the instantaneous rate of change. We don't have enough information. And that's why the question's asking us to estimate, but not find it exactly. If we want to estimate the instantaneous rate, or the slope of a tangent line, what do we usually use? Yeah, we use the average rate of change, and we try to pick a small interval that's close to 12. Visually, think of it this way. As the temperature is increasing, at 12 seconds, the temperature is some particular number, and it's increasing at some particular speed, which is represented by the tangent line. That's the instantaneous rate. Since we can't figure out what the tangent line is, instead of calculating the slope of that green line, we're going to take a point on either side of 12 and connect the dots to create a secant line. Notice how the slope of the secant line is pretty close to the slope of the tangent line. That's how we can estimate it. What does this mean when we're working with a data table? Well, take a look. We don't know exactly what's happening at 12, but we do know something about the interval that includes 12. Using the 2 points, 9, 61.8, and 15, 67.9, we could calculate the slope of a secant line on a small interval close to 12. It would look like this. y2 minus y1 over x2 minus x1. And since this is a rate, we would want units for it. If we take the units for y over the units for x, that would be degrees per minute. That's A, not so bad after all. Okay, let's look at B. B is where the integrals come into play. It says use the data in the table to evaluate this integral and interpret what it means. Just like before, we want to start by annotating anything that you understand about the meaning of what you're trying to find. What do you know about what's in the screen? Exactly. This just means the area under the derivatives curve between 0 and 20 on the x-axis. Well, you know something else about that. When we're looking at a curve that's a derivative function, the area under the curve is the same as the net change in the original function. In other words, w prime of t being the derivative, this integral, according to the fundamental theorem of calculus, must equal the original function evaluated at 20 minus the original function evaluated at 0. And those two numbers are just numbers from this table. The original function evaluated at 20 is 71, and the original function evaluated at 0 is 55. So actually, evaluating this integral really just means I need to subtract the 2, which gives us a total of 16 degrees, because it's a change in amount of degrees. And then we just need to explain that this number represents the total amount by which the water or whatever we're heating increased over the course of the first 20 minutes. It would be important to say over the course of 20 minutes. Since I'm at the end of the time here, we'll pause and continue.